I have 4 examples here of integral evaluations, and I'm going to tie that at the end of each problem to the graph it represents. All right, but the integral itself is just taking the antiderivative of the function, and we know that we can do this. The antiderivative of 6 is 6x over 1. We're going to evaluate that from -2 to 5. This is a definite integral. It has evaluations. We can plug in 6 times 5 minus 6 times -2. 30 minus 12 is an area of 42. And you caught that, hopefully I said area, because this curve, if I go back to the very beginning, the function is 6, which we recognize as a horizontal line. And it had the integrals from -2 to 5. Maybe not the scale here, but what I want you to understand is we have just found the area under this curve from -2 to 5, which is a distance of 7 and a height of 6. Well, obviously the area of that rectangle is 42. Quick check. All right. And again, as we do these examples, you can pause and make sure you're getting the right answer. We're also going to graph each of the situations at the end. The next one. Integral from 1 to 8 of the cube root of x. First of all, I'll make it fractional. Add 1. I always go through these steps. And again, this is a non-calculator problem. I can kind of tell because the 1/3, 8 to the 1/3 is 2, and 1 to the 1/3 is 1. So we'll do this, and I'll pull the 3/4 out, put parentheses, and I'll subtract the difference, and I have 8 to the 4/3 minus 1 to the 4/3. And in my head, I picture this, whoops, let's think it too, 8 to the 3rd, from 4 here, 8 to the 3rd to the 4th, well, 8 to the 3rd to 2, 2 to the 4th is 16. So I get 16 minus 1, which is 15 on the inside. Still times the 3/4 on the outside. So I get an answer of 45/4. Now this is a case where I'm not going to be able to figure out the exact answer like the other problem. But again, we're pretty good with graphing these type of functions, and we recognize cube root of x as this function. And we have found the area from 1. I suppose 1 would be a little closer as the equal distance, 1, 1 to 8, 2. And we found this area right here under the curve, be 45/4. Again, a visual representation of what the integral does. It gives the area under the curve of the original function. Next one. A little bit more complicated. Take the integral from 0 to pi over 4 of secant squared theta d theta. All right. Again, I have memorized my derivatives. And I know the derivative of tangent x is secant squared x. So when I see secant squared x, I think backwards here to get the integral. So I immediately recognize this is tangent theta, integrated from 0 to pi over 4. So tangent of pi over 4 minus tangent of 0, pi over 4, tangent pi over 4, 45-degree triangle, 1 over 1, minus sine over cosine, it is 0. So the area of this curve, of that curve, is 1. Drawing the curve is a little more complicated. And I'm going to have to start with pi over 2, 0, pi over 2. And I'm only working to pi over 4. Put those in. And I have to build this personally off the cosine curve, which I know looks like this, and it's not really to scale. Got a little out of scale on the x. And I know the secant curve then builds off of this. boom, and looks and approaches the asymptotes that secant has, because cosine is 1 over cosine. And if I square that, it's still 1 squared. It just gets bigger faster. So this is the curve, and I'm going from 0 to power 4. So I know this is searching for the green area under the secant squared curve. Again, the answer is 1. It's fairly straightforward, but we want to picture not only the answer, but what the graph looks like also. Last one, parabola, x squared plus 6 dx, integrate from -4 to 4. Big thing in here is you can do the integral right away, but one of the things I'm going to do is, if this is the area of the curve, we should recognize that I can do this, because this is an even function. All right? I'm going to do it both ways. I'm going to pause the video, but I'm going to just do it this way here. This is going to make our lives much easier. All right? So again, I get x cubed over 3 plus 6x over 1 from 0 to 4. When I take the antiderivative of the integral 2 times, and again, 4 cubed over 3 plus 24 over 1 minus 0 plus 0. So I get 2 times. And if I use my calculator, I get 90 and 2/3. And again, I'll do the graph before I do the integral from -4 to 4, because we should recognize this as a parabola going like this through the y-intercept of 6, -4 and 4. We keep it to scale. What we just found is this area underneath. What we did, though, is we cheated and doubled the red area. All right? If you want to do the integral from -4 to 4, the only change is at this step right here. Well, obviously, the limits of integration change, and we lose the 2. So if I went from -4 to 4 of x squared plus 6 dx, I would get x cubed over 3 plus 6x over 1 from -4 to 4. Okay, and the only difference that makes is that I end up with 4 cubed over 3 plus 24 over 1 minus -4 cubed over 3 minus 24. And you notice the negative is going to make a positive. It just doubles like the graph would show. All right. So again, when we see functions and we can picture what's going on, we can save ourselves quite a bit of math. All right. Keep practicing. Definite integrals, area under the curve.